Okay, good. Yes, atoms and semiconductor. Breakfast over. Okay. Now, what about other things? Everything going on good? Okay. Now, so today we are having atoms as well as semiconductor. Atoms and semiconductor, not complete semiconductor. Half part of semiconductor we are having. Up to PN junction diode we have to do. Okay. Up to PN junction diode means forward biasing and reverse biasing. Up to that we have to do that thing. Okay. So in this one, atoms, I think we all are comfortable with atoms. Yes. In atoms, we are comfortable because atoms is the one small thing. In semiconductor, I feel that at that time, semiconductor we have not done. Okay. One quick, yes, quick revision we will do for atoms also. But mainly we have to focus on what? Means I'm asking to you, whatever you want, we will do that one. Means atoms or semiconductor. Whatever you will say, we'll start that one first. Which one we have to start first? We'll start that one. Semiconductor, people are saying more. Why people are saying semiconductor more? Reason is because at that time, okay, we did, but it was not, I think, perfect. Somewhat fast way we have done. Okay. So now we'll be doing that one. And atoms also we will do. Okay. Atoms. So in half an hour, we will do the important things of atom and okay, energy levels related to that. And okay, in semiconductor will be starting now. So listen, in semiconductor, there are so many things that I cannot, because all the things from the basics we cannot write. Okay. So here I will be asking few things like, we know what are the semiconductors. Okay. First thing everyone knows about these things. Okay. That there is one valence band and one is the your conduction band. Okay. This is the basic things. What are the basically this VB? VB is known as your valence band. And this is the CB is the basically your conduction band. Now, what is the meaning of these band here? Band means basically when we are having one energy level, okay? When we are having one energy level like this, okay, like this. So when one level is there, that we can say this is the energy level, okay? And when we are having set of energy levels like this, then set of energy level becomes your band, okay? When one atom is there, then we say that is the energy level, okay? When one atom will be there, that is the your energy level. And you know, in solids, like we are talking about your silicon, there will be the how many atoms? There will be a huge number of atoms. And when huge number of atoms are there, then all combined energy levels are known as your band. So if anyone is asking what is the band, basically, band is nothing but the set of energy levels. Okay. This is nothing but the set of energy levels because you will be having n number of atoms. So n number of energy levels will be there, and when n number of energy levels we will combine, then these are basically known as your band. Okay. Now, so valence band is there, in which valence electrons there, in which valence electrons are there. Okay. In which valence electrons are there, that is known as your valence band. Okay. What is meaning of conduction band? In which conduction electron, or we can say free electrons are there, okay? In which free electrons exist. You know, valence electron and free electron, which will be having more energy here? Free electron or valence electron, which is having more energy? Of course, free electrons are having more energy, okay? So this energy, okay, here, in this one we are having basically, this is the set of energy levels, lot of set are there, okay? Set of energy levels here, okay? And in this one also we can say set of energy levels here, okay? But ultimately what happens in this one, Okay, that this conduction band will be having, this band will be having more energy, this will be having lesser energy. Okay, because these are your bounded electron, or we can say these are your valence electron. This gap is known as your delta Eg. Okay, this gap is your delta Eg. Clear? This is known as our forbidden energy gap. Okay, now generally electrons are there in conduction band or valence band. Generally electrons are in your valence band. Okay, valence band. Okay, but in metals what happens, and metals this gap is either very less, or valence band and conduction band there is no gap in metals. Okay, in metals what happens, I will draw here. In metals what happens, that situation will be like this. We can draw here. Situation will be like this. This is the our okay, valence band, and here, okay, this is our conduction band. And you can see here that between conduction band and valence band there is no gap, or there is some overlapping also. What is the meaning of this thing overlapping here? Okay, what is the meaning of overlapping? Overlapping means already few electrons are free. Okay, is some electron of valence band are already in your conduction band, means some are already free. Okay, some are already free, so some overlapping is there between your conduction band and valence band. You can feel here, because of this some electrons are free, like we have in sodium. Okay, one free electron is there. We are having your second group, we are having your two electrons are free. Okay, so they are behaving like your metals. In semiconductor what happens, this gap is less. Okay, gap is there, but that gap is less. Is here we can say the Cb, this is the Vb, and here we are having this gap is your delta Eg. This delta Eg is around 1 electron volt. Okay, around 1. It is not, okay, is for silicon we know this gap is 1.1 electron volt, and for germanium this is the, we can write delta Eg. For germanium this is the 0.7 electron volt. Okay, around 1, or we can say less than 3. Okay, less than 3 also, around 1. Next thing we can write here in this one, next thing becomes your insulator. In insulator what happens, this gap is huge. This gap is more than 3 electron volt. Like we can say for diamond this gap is around 5.5 electron volt. Okay, this gap is huge. Now you know that if gap is huge, then what happens? If gap is huge, then they need very high energy to, okay, very high energy is required to transfer electrons from valence band to conduction band. Here we can check how much energy is required. Okay, 1.1 is required for silicon, 0.7 is required. This energy is available at room temperature, but here 5.5 is not available at room temperature, so here electrons cannot be excited to conduction band. Okay, that's why this thing are behaving like your semiconductor. These are the conductor because already some electrons are free, already they are in the conduction band. Here gap is huge. Clear? Now I will ask one question here, means you can find for silicon that if you want to find lambda, then we have this formula 12400 divided by 1.1. If you calculate here in this one, we can write, so this will be coming how much? Approximately we can say 11,000 angstrom. And 11,000 angstrom is basically in which range? IR. Is IR, infrared radiation, can send this one to your okay, here in your conduction band, we can easily send this one. So using our whatever at room temperature, you know, because of temperature, whatever radiation exists, that radiation is your infrared. So using infrared also we can transfer. But in case of diamond, if you want to consider, so we can, lambda will be equal to 12400 divided by 5.5. Can you tell me approximately? Approximately? Just approximately I'm asking here, how much lambda is required for this one? Just approx value. Around 2000, someone is saying. Yes, around we can say 2000. And 2000 is basically in which range? It is in your UV range. Okay, means at room temperature you cannot get, using IR we cannot get this thing. It is in your UV range. So diamond we cannot excite. Okay, so now I will be asking one question here. Okay, question is here: band gap for a material is 2 electron volt. Find which wavelength which wavelength can transfer electron from VB to CB. Okay, VB to CB. Okay, and they have given here in this one A option, B option, C option, D option. Okay, what is the answer? Listen, we have to calculate here by this lambda equal to 12400 divided by 2. Okay, now then we can write here, this thing becomes your 6200 angstrom. Okay, 6200 angstrom. So answer is not only 6200. Okay, here we do mistake. They are saying which wavelength can transfer electron from VB to CB. VB to CB means if you want to transfer VB to CB, then 6200 you can use. If you use somewhat more energy, then what happens? If you use somewhat more energy, then what happens? Yes, if we are using somewhat more energy, then what happens? Of course it will transfer. Lesser wavelength means more energy. Lesser wavelength, more energy is that can be also used. Okay, lesser wavelength means more energy, that can be also used here. So can I use 6000? Yes, 6000 is less than this. More energy, it can be used. It can be used. 4000 is less. It can be used. This can be also used. We can use all. Okay, we can use all to excite this. Clear this one? Yes. Okay. Second question I will ask. I will give you that this wavelength is able to transfer. Then what is the band gap? Okay. Question will be like this: that if 4000 angstrom, this is the second question, is just able to transfer what is gap? What is band gap? Just able to transfer means this is okay, our limit. Okay, 4000 is just able to transfer, so we can say in this one lambda will be equal to how much? 12400 divided by your 4000. So you can find band gap from here will be 3.1 electron volt. Okay, these are the questions related to your band gap here. I hope this thing is clear. Can we go for next? Okay, now we are having types of semiconductor. One is the your intrinsic, one is the extrinsic. Intrinsic as well as extrinsic. Okay, intrinsic is your pure form of silicon and germanium, completely pure. Okay, in completely pure silicon and germanium, what happens that when we are having, okay, intrinsic means it is the pure form of silicon and germanium. In this one, conductivity will be more or less. Conductivity is very, very less. What is the reason for this one? Because here we are having, this is the silicon in this. Okay, silicon is making 4 bonds, and when silicon is making 4 bonds here, then everyone knows in this one, okay, at room temperature, means at 0 Kelvin. If they are asking at 0 Kelvin, then at 0 Kelvin any bond, there will be any energy to break the bond. At room temperature, there will be any energy to break the bond? No. Okay, means we can say here in this one, okay, they will be asking, so we can say here, okay, balance band, how many electrons will be there in balance band? How many will be there? We know 4. Okay, in balance band 4 will be there, but for one atom. But there are how many? n number of atoms. So there will be the 4n electrons in valence band. In conduction band, how many will be there? 0 electrons. Okay, at 0 Kelvin. Okay, at 0 Kelvin means at 0 Kelvin there is no energy to break. So balance band is having 4n. Okay, 4n, and conduction band is completely empty. It is completely empty. Okay, so you can write at 0 Kelvin, valence band 4n electron, and Cb is your 0 electron at 0 Kelvin. Okay, there is no energy to break. But what happens at room temperature? At room temperature, due to temperature agitation, okay, due to temperature agitation means due to temperature vibrations, we can say due to temperature agitation. Now, due to temperature addition, what will happen? Your okay, here some bonds will be broken, and suppose this bond is broken here, so your electron will be free. An electron will be free, so I can represent here. Okay, this electron is free. What is created here? Hole. Okay, so temperature agitation, electron hole pair created. Okay, now so here we got suppose three holes. Then how many electrons we got? Three electrons. Okay, this is the conduction band. Conduction means these electrons are now moving with more energy. Okay, three electrons. These are the three holes. Okay. Next thing in this one, you know that here also bond is broken. Here then bond is broken. But in this one, out of 10 power 8, 10 power 8 atoms, one electron hole pair will be created. Okay, and one is created, so conductivity more or less. So conductivity is very less. Okay, conductivity is very less because out of 10 power 8 atoms, only one electron hole will be there. So conductivity is going to be very, very less here. Okay, now next thing we can write in this one here. So to increase conductivity, doping of trivalent or pentavalent. Okay, doping of trivalent and pentavalent we are doing. Okay, when you're doing doping of trivalent, then it will become your which type? Impurities are added. Okay, impurities are added. That is known as your doping. Doping is addition of impurities. Trivalent, then it becomes your P type. We will be having that in detail. And when pentavalent is there, then it is known as N type. Okay. So these are known as your extrinsic. Okay, extrinsic means what is the meaning of extrinsic semiconductor? Extrinsic semiconductor means to increase conductivity. We are adding some impurities, and these impurities can be trivalent for P type or can be pentavalent for N type. Okay, this is known as doped silicon or germanium, and or we can say your extrinsic semiconductor. Intrinsic is the purely silicon germanium, and extrinsic is the silicon germanium plus some doping is there. Something we are adding, some doping. Okay. Yes. Clear? This thing here. Here, if you see that doping thing we will do, okay, here later on. In this one, we can find here Ne equal to NH. Okay. So in this one, there is no one can ask what is the major, what is the minor. Both are exactly same. Okay. This is and this exactly same. And here we can say average energy level is exactly at middle. Okay. Fermi level or average energy level is exactly at middle here. Okay. Because both number are same. We can say N equal to NH equal to, this is known as your Ni. This, what is the meaning of Ni here? That is the here intrinsic concentration. Intrinsic concentration. Then we get Ne into NH will be equal to Ni into Ni. So it is the Ni whole square that we will use. Okay, in our questions. Now, yes, Ne into NH equal to this thing. Listen, In this one, we have to remember that because of conductivity is very less, because out of 10 power 8, one electron hole pair is created. So we need to mix something. N into NH equal to Ni whole square. Okay. Now what happens? Suppose here hole is created. Okay. Then, okay, here lot of silicons are there. Lot of silicons are there. Now what happens? Suppose this electron finds here, and this electron is not happy with this bonding here. If this is not happy, okay. So if this electron find that there is the vacancy, so this electron will jump here, will fill this vacancy, and hole will be created here. So actually you can say hole moved from here to here, but actually hole moved or electron moved? Actually your electron moved, not the hole. Okay. Now similarly we can say, suppose this bond is broken, but energy is not equal to that of free electron, or energy is lesser than the conduction band. Okay, energy, because bond might be electron is ready to break the bond or electron is ready to move, but energy is somewhat less. So here, if this electron finds that there is one vacancy, this electron will go here and then hole will be created here. Okay, so like this hole is moving, but if I ask hole is moving or your electron is moving, actually hole is your virtual positive charge. Hole is nothing but the virtual thing. Hole is the deficiency of electron. Hole is nothing but the deficiency of electron. Okay, hole is nothing but the deficiency of electron, means hole is what? You can write somewhere, hole is deficiency of electron, and hole is virtual positive charge. Because of this, hole is virtual positive charge. Hole is virtual positive charge, or we can say deficiency of electron. Okay. Now, movement of hole is nothing but the movement of free electron or movement of bounded electron. Movement of hole is nothing but the movement of bounded or free. Listen, if this becomes free, this is moving in conduction band. Okay. And this electron is basically your bounded electron here. Bounded electron finds that here one hole is there. So, okay, same thing is there, that you are here, okay, you are settled, okay, in your classroom. I will say like this, then you can easily get. Suppose you are in classroom, okay, and in classroom we are all are there, okay, B plus G, everyone is there, okay. Now, what happens that if you get suppose 500 rupees, then what happens? You will go out of the classroom. You will go out of the classroom. You will be going somewhere. Okay. You will move in campus. You will go to your canteen, and you are free now. Okay. Sometimes what happens, when you will see that first row, in first row, one student have moved out. If one have moved out, so from the middle row or from the last row, you will come and you will sit in the first row. It happens. If first row student gone outside of the class, then what happens? That here in the first, okay, second row or third row or fourth row, okay, some student will come and then it will fill this vacancy. So where vacancy will be created now? We can say in third line vacancy is created. Okay. Now someone at the fifth row will see this thing, and then he will come at the third, and then your vacancy will be filled here. Now hole is created in the fifth. Now from the backbenchers group, okay, from the backbenchers, someone might be coming here and then fill the, okay, this hole, and where hole is created at the back side. Now you got, so hole is moving, means it is not because of free electrons are filling or your bounded electrons are filling. Just bounded electrons are filling. These are not filled by free electrons. Clear? So movement of hole is movement of what? Movement of hole is movement of, yes, bounded or free. Tell fast. Whatever you say, bounded. Okay. Bounded. Free electron is moving everywhere. Free electron means now you are free. You are going to canteen. You are going to girls' hostel. You are going to Puranki. You are going to anywhere. Okay, you are free because. Okay, but inside the class also there is the movement. Inside class, your electrons are moving. That are the basically our bounded electrons. They are moving, and because of that, our hole is moving. This hole is not actually moving. Hole is actually not moving. Who is moving? In place of hole, actually bounded electrons are moving. Okay. Who is asking this? What is your name? You don't know my name and still came here. Very good. Now, question is here that movement of hole is basically movement of electrons. Okay. So you can how to write here movement of means movement of whole is movement of what? Bounded electrons. Okay. Bounded electrons. Now, bounded electrons will be moving with more energy or will be moving with lesser energy. Moving with more energy or lesser energy. Bounded are moving with lesser energy. Okay. Free are moving with more energy, which require lesser energy to move. Bounded or free. Bounded basically are moving with lesser energy. They need lesser energy to move. Which will be having more mobility? Which will be having more mobility? Bounded or free? Of course, free will be having more mobility. So we say which are going to have more mobility, holes or electrons? Which have more mobility? Holes or electrons? What is the answer? Electrons have more mobility. Okay. And what is the actual reason for that? Why electrons are having more mobility? When we say electrons, means we say free electrons. When we say holes, we say our bounded electrons. Okay. So this thing is clear. Holes means bounded electrons. Okay, that is the background. Okay, we say always whole. We will say whole. Okay, we are habitual of whole. Okay, but we'll feel that this is the bounded electrons. Okay, so you can write mobility of electrons. Mobility of electron is more than holes. Mobility of electrons is more than holes. More than holes. More than holes. Because holes require more energy to move or less energy to move? Because hole require less energy to move. Okay, because hole require less energy to move. Write it fast. Holes require less energy to move. Okay. Now next thing, less energy to move. Okay. So these were the basically in this one. Okay. Now when you will apply some electric field, what happens? At present, all are moving randomly. Okay, your electrons also moving randomly. They are going anywhere. Okay, holes also moving randomly. So there is no one particular movement. So are we getting any current here? We will get current when we are applying some external field. Some field we need to apply. Then only they will move. Okay. So when we will apply the field, okay, then what happens? Your electrons will be moving and holes will be moving. Okay, suppose I have applied like this electric field in this direction. Okay, you can apply in any direction, your choice. Okay, this is okay. Suppose I have applied like this, then you know electron will be basically moving opposite to this. Electrons will be moving opposite to this, and holes will be moving in the direction of this. So if I say direction of current here, then we can say direction of current for the electron will be your. For the electron, we know it will be opposite to this. Opposite to movement of electron means we can say this current will be your IE. For the hole, it will be in the same direction. So this is the IH. So what is the total current? We can say it is the your IE plus IH. Its total current is because of electron plus hole IE plus IH. Any problem here? Yes, over. Okay. Zener diode will be in your okay next syllabus, not this week's syllabus. That will be coming in next week. That will be doing perfectly. All the things will be doing perfectly, no problem. Okay. Over hydrogen current is because of both IE plus IH. Now I'm coming here in this one. That is your okay P type. P type means you know here we are going to mix your silicon germanium plus in this one trivalent or pentavalent. Trivalent, okay, just like your aluminum. Okay, so when you're mixing trivalent, okay, one thing they are asking that how much you can mix, and why you are not mixing your okay, you are mixing third group and fifth group, why you are not mixing second group, first group, or this side. Okay, reason is because in this classroom, if we are having fun, we are having party after selection. Okay, Okay, you can take a screenshot. Take this. Take it fast. Done. Now, listen. What I'm asking here, we having here party. Suppose someone mixed here, okay, a small kids in our classroom. Then what will happen? You will be disturbed or you will be having fun. Of course, you will be disturbed. Okay. And if suppose they mixed, okay, they mixed your vice principal, previous one, okay. Then what happens? Then also you will be disturbed. You will be disturbed, na? Where you will have more fun. You will be having more fun when your friends joins the party. Already you are having here fun, and if your friends joins the party, it's similar to you. If similar to you people are coming, then we'll be having more fun. Okay. So similar things are there. That whatever you are mixing, I know. Okay, whatever you are saying. Okay, when someone joins party, I know. Okay, but I cannot say. Few things I cannot say. Okay. Whatever is there in your mind, I know. Okay. Now, whatever means here question is that whatever we are mixing, size of that must be similar to our silicon and germanium. It should be okay similar, and you cannot mix more. You cannot mix more. Why we cannot mix more? Because if you mix more, then ultimately, okay, our lattice will be changed. Like we having 100 silicon germanium. In 100 silicon germanium, you are mixing suppose 1,000 impurities. So 1,000 impurities, if you mix, then we can say this is the lattice of impurities. Okay, so we cannot mix more. We have to mix somewhat less. So you can write somewhere size of impurities should be similar to silicon and germanium, should be similar to silicon germanium, similar to silicon germanium, and doping level is 1 ppm. Doping level is 1 ppm. Okay, what is the meaning of 1 ppm? Basically part per million. Okay, out of 10 power 6 we need to mix one, okay, one impurity. Out of 10 power 6 we need to mix one impurity. Okay, that is clear. One impurity we have to mix. Out of 10 power 6 we need to mix only one impurity, that is the part per million. Now, so you know that in this one, silicon is going to have your 4 bonds with each other. Okay, there are the 4 electrons, they are going to make 4 bonds. When aluminum will enter, aluminum is having only 3 electrons. So max to max, how many bonds it can form? It can only form 3 electrons. Okay, now it want to form identical, okay, it want to form identical bonds. Identical bonds means 4 bonds, because everyone is having 4, it also wants 4, because in the party everyone is having 4 bonds, it also want to form 4 bonds. To form 4th bond, it needs basically 1 electron, but 1 electron is not available for us. For this aluminum, it is not available. Means one thing we can do, that because of temperature, this is the valence band, this is the conduction band. Because of temperature, we are getting some holes and some electrons. So why we are getting some holes and some electrons? That is your because of temperature. Because of temperature, some electron and holes are always created, but the number is very, very less. Number is very, very less. So we have added aluminum. Now what happens? This aluminum will find that this, okay, this silicon is holding its electron very loosely, okay, very casually it is holding. So it will snatch electron from there. This will snatch. So when it will snatch electron from here, then it will form the bond, and here what is created? Your hole. So one aluminum will snatch electron. Whenever it find that one electron is, okay, we can snatch easily. From where we can easily accept. Okay, clear? Easily. Okay, so here it will form the bond, and now this becomes acceptor or donor atom. This aluminum, this becomes acceptor atom. Now, acceptor atom, if I ask, after accepting electrons, it will be positively charged or negatively charged? It will be your positively charged or negatively charged. We can say it becomes your negative charged. Okay. After accepting, it becomes negative charge. This aluminum. Okay. Listen, this aluminum is mixed. Aluminum want to have how many bonds? 4 bonds. Okay, because in everyone in party is having 4 bonds. So this also wants 4 bond. It is having 3 electrons. So it will be looking for fourth electron. And from where it will get the fourth electron? In the lattice, in the party itself. In the party itself, he will find, he will search, okay, whose bond is somewhat loose, whose bond is somewhat loose, and if your bond is somewhat loose, he will take electron from you. Okay, now take an electron from you. So what happens? Yes, we can write here in this pen, its bond will be formed, okay, and their hole will be created. Okay. Yes, billionaire, you are correct. Now, so we can say here, one aluminum is going to create one hole. Okay, one hole. Similarly, if I have mixed 1,000 aluminiums, if I have mixed 1,000 aluminiums, then 1,000 aluminiums will create 1,000 holes. So here we are going to get huge number of holes. Okay, huge holes. So we are getting huge holes in this one. And why we are getting huge holes? Because of acceptor atom. Okay, so if anybody is asking what are the major, then major we can say major are the holes. And why holes are the major? What are the reason for this? Why holes are the major? Because of acceptor atom. Okay, because of acceptor aluminum atom. Okay, minor is your electron. And why minor is the electron? Can you tell me, region? Why electron is minor? Electrons are the minor because they are created because of temperature. Minor is always created because of temperature. Clear? Earlier we were having your some electron and some holes. Minor is created because of temperature. Majority are created because of doping as well as temperature. But because of temperature, it was very, very less. Now, if I say energy level of acceptor atom, if it want to accept, so it is accepting from valence band or it is accepting from conduction band. From where it is accepting? It is accepting from where? It is accepting from valence band or conduction band. Aluminum is accepting electrons from where? Means it is taking free electron or it is taking boundary electron. It is basically going to snatch boundary electron. Okay, so it is taking from where? Valence band. So energy level of acceptor should be close to your valence band. This one you have to remember. You can write somewhere. Energy level of acceptor atom is close to valence band. Valence band. Okay. Now, in silicon, if I say here, you can see in this one. Okay. Total gap was how much? Total was for silicon, if I say for silicon, total was 1.1. So, you know, this was 0.55. This was also 0.55. Both were 0.55 because it was in middle, okay, in intrinsic. But here, if I ask energy level of acceptor atom from VB, energy level of acceptor atom means energy level of acceptor atom EA from VB. So EA from VB will be your less than 0.55 or more than 0.55? Less than 0.55, because this will be now less than 0.55. This is clear? It will be total is 1.1. Okay, total is 1.1. Middle is what? 0.55. Okay, so it will be less. And if I ask energy level of acceptor atom from CB, then from CB, what we can say? From CB, it will be your more than 0.55. Okay, more than means here this will be more than 0.55. This will be less than 0.55. Okay. Now, next thing we can write here in this one. Here current will be because of both. Means we can write here Ne into NH will be equal to Ni whole square. Okay, but here NH is mainly because of NH is mainly because of your acceptor atom, Na. Holes we are getting mainly because of acceptor atom. We are getting huge number of holes because of acceptor atom. So we can write here in this one, Na will be equal to Ni whole square by Na. How they are going to ask question on this one? They will be giving Ni will be given to you. Na will be given to you. Na means how many aluminum we have added. That thing will be given to you. And Na will be asked. And we can easily find here. Okay. Na will be asked and we can find. Clear? Just read the numerical question. Just you have to put the values. They will give intrinsic concentration. They will give, okay, your acceptor atom, or they will say that aluminum, this much aluminum is added, and then we have to calculate this. Here we can say total current is because of IE plus IH. Okay, but we can say approximately current will be because of holes, because IE will be very very less, because your minority, so minority will be very less, so majority we are getting current because of IH. Clear here? Yes. Now can we take next thing now? This is the your okay thing about your p type and then n type. Okay, we need to do somewhat fast. Now in this one they ask that if temperature increases, okay, and listen, don't rely on your screenshots, just you can write important things, that will be much better. Okay, don't rely on a screenshot. Some people are saying, okay, because if you're taking a screenshot, then you know that we never see that one again. So it's better that we can write whatever things are, okay. Already we know a lot of things. Whatever things you don't know, you can just update that one, okay. So it is always better like this. Now here we are having, if temperature increases, then they will be asking Ne by NH. Okay, so we know Ne by NH will increase for p type. Okay, Ne by NH will be increasing for p type. Why? Okay, I will tell you one example for this. Suppose in p type, everyone knows electrons are, suppose here how much? We can say 1, and holes are how many? Holes are your, suppose 100. Okay, you know that electrons are less and holes are more. Suppose if I say we want to prove this same thing for n type, then n type you will take more electrons and less number of holes if you want to prove. Okay, so here I have taken p type. So like this, if due to temperature 10 electron hole 10 electron hole generated. Okay, if 10 electron hole generated due to temperature, so we can say any dash will be equal to how much? 11, and NH dash will be how much? We can say 110. Yes, 10 are generated, so 11 and 110. Here if you find Ne by NH, so we can say Ne by NH is here what? Initial ratio was 1 by 100, but now if you find Ne dash by NH dash, so this ratio becomes 11 by 110. That is your what? 1 by 10. So this ratio is increased or decreased? This ratio is increased. Okay. If you want to derive this thing for your n type, then in n type what happens? You will take reverse here. So everything will be reverse, means in that case it will decrease. Okay. It will decrease. So now I'm going to write your n type. I hope this thing is clear here. You have to remember, they will ask that if temperature increases, then Ne by NH, then we can know Ne by NH will decrease. Means here it will increase, in n type it will decrease. Now, if I say n type, listen, in n type we are mixing your silicon, germanium, plus this is the your pentavalent. Pentavalent examples, I think you know. This is the, we can say, phosphorus, arsenic, like this. Okay, now they having a, this is the silicon here. Silicon is making 4 bonds. So in the lattice of silicon, if you mix here, suppose phosphorus, this phosphorus is having your 5 electrons. So using 4 electrons, what it will do? It will make the bond, and 5th electron it how to donate. Okay, 5th electron is okay, 4 it will make the bond. Means using the 4 electrons it will make the bond. Now 5th electron will say, if you are not making bond for me, I will go outside. Okay, in the party 4 are engaged. If 4 are engaged, 5th will say, I want to engage myself. This Phosphorus will say you cannot engage here, but only 4 can be formed. So this, what fifth one will say? Fifth will say, I will go from the party, and it will be going away from the party, means it will become free basically. So here one electron will become free. We can say conduction band, we can say valence band. Some electrons and some holes we are getting because of temperature. Okay, some electron and some holes we are getting because of temperature. Clear? Now, this phosphorus, one phosphorus will donate one electron. Suppose I have mixed here 1000 phosphorus, then 1000 phosphorus will donate 1000 electrons. So here electrons will be huge. Okay, electron becomes huge, and if you know that electron become huge, if there are so much electrons, so many electrons here, then everyone knows in this one, okay, so many electrons are there. So we can say major is the electron here, minor is the hole here. Okay, minor is the hole. This becomes your donor or acceptor. Here it becomes donor atom. If I ask, donor atom will be positive charge or negative charge? Donor atom becomes positive charge. Listen, everyone remembers that what is the major, what is the minor. They forget about your this donor atom or acceptor atom. You know that electron can move easily. With respect to electron, your phosphorus or aluminum, size of phosphorus and aluminum is small or very large. Like electron is this, then size of phosphorus is very large. If size of phosphorus or aluminum is very large, it can move, it cannot move within the lattice. So this is known as your immobile ion. Okay, immobile ion means it cannot move. Okay, so they will ask in p type. In p type contains positive immobile ions or negative immobile ions. P type contains positive immobile or negative immobile. P type, I'm asking for P type. You can see P type contains what? Here, P type contains negative immobile. This aluminum is the basically immobile, negative immobile ions. Okay, in P type. Majority, minority, you know, people do mistake here when they are asking this thing. N type contains, we know N type contains what? Positive immobile ions. It contains positive immobile ions. Overall charge is neutral, because you know positive and this electron, positive electron is neutral. Okay, so overall semiconductor is always neutral, but positive and negative immobile ions are there. Okay, somewhere you can write overall semiconductor is neutral. Okay, semiconductor is neutral. P type contains positive immobile ion, means N type contains positive immobile ions. If I say donor levels, it how to donate to conduction band. So donor level should be close to, energy level of donor should be close to what? It should be close to conduction band. Okay, it should be close to conduction band. Okay, clear? So there are the three things here you got. Okay, you can write donor level should be close to conduction band. One is the majority, one is the minority, and one is the your immobile ions. If I ask in P type, what is the major? In P type, major is the hole, minor is the electron, and immobile ions are positive or negative? Negative immobile. Okay. Here we can say in this one, major are electron, minor are hole, and immobile ion is positive, negative, immobile ion is positive. Okay, these are the things. Yes, Oppo, what you want to ask? Yes, forward bias. We are going to just start right now. Okay, we'll be starting forward and reverse within 5 minutes. Oppo, what was your doubt? Clear this thing? Now, here we can say in this one, number of, okay, your electrons are mainly because of donor atoms. So we can write Ne into NH, that is the Ni whole square, and here we can write your NH will be equal to Ni whole square by Nd. Here current will be mainly because of, current is IE plus IH, but mainly we can say current will be because of what? IE. Okay, means in this N type. So you know which current will be more? P type. In P type current will be more. What is donor? This is not donoration yaar. This is the donor atom written here. Donor atom. Donor atom means which will donate electron. Okay. Clear? Now, listen. If it want to donate, okay, and its energy after, okay, it can only donate to the conduction band. Means it can donate. What is the meaning of donation? Means its electron will become free. Its electron will become free. When it will become free? When energy of this okay, this electron which want to become free, if energy of this electron is equal to the other free electrons, equal to the your conduction band. If energy is equal to the conduction band, then only it will reach to conduction band. Yes, if it's slightly less, some energy it can get from temperature also. Some energy it will get from temperature also. So if energy is slightly less, and some energy it can get from temperature, it can easily go to conduction band. Like suppose conduction band, to reach conduction band, it needs 100. It needs 100. It is having your 80. It is having 80. So 20 energy it can get from temperature, then it can easily reach. Okay. But suppose this is having 20, it is having 20. It can get that much energy using temperature. Now it cannot go. So here energy should be close to which band? Energy should be close to free electrons, close to conduction band. And if somewhat less, okay, somewhat less, then it can okay, get that this much less. Okay, so this much less it can easily get using the temperature, because we are talking at room temperature. At room temperature, this much energy it can get. So here to here it can easily transfer. But suppose if you take here, then what happens? If you take here, suppose this is the your donor atom, and it needs this much energy to go here. This much energy using temperature is not available. So it should be, this donor should be close to valence band or should be close to conduction band. Now it should be close to conduction band, then only it can be easily transferred. Okay. At room temperature, some thermal energy is always available. That thermal energy is not huge energy. It is a lesser energy. Okay. So it should be very, very close to the conduction band. Then it can easily transfer. I hope now this thing is clear. Yes, Anish. If anyone having doubt, I will okay, because now we need to do a lot of things. Over, clear? Yes. People are just okay. Yes. Now we'll be writing next thing now. Okay. In this one, we can say here